We are recording. Okay, so welcome back. Today's lab is about igneous rocks, or rocks that come from magma. And this is actually one of my Iceland pictures. This is a lava field in Iceland. And if you look in the background in the middle, you can see the cone from which all these lava flows originally came. So these lava flows are full of basalt, which is a type of igneous rock. And that's one that you'll see in lab today. So this lab continues the mineral and rock trays labs. And normally you would actually be physically in a lab looking at trays full of igneous, full of rocks formed from magma, as well as some large samples of the minerals that normally make up those rocks. And there's going to be several similar labs after this focused on sedimentary rocks and metamorphic rocks as well, but not next week. Next week is spring break. And so I am setting the due date for this lab to be the Monday after spring break. So that's Monday the 15th, if I have that correct. And that's also when a quiz on minerals from last week is going to be due, now that you've completed both parts of the minerals lab. And also, if you're missing other work, this is a good time to get caught up on that. So please let me know when you submit any assignments, or if you take a second attempt on any assignments to fill in, say, something you left blank before. But there's no lab next week. So you've probably seen a similar chart to this before, but here is the rock cycle. And there's three types of rocks we're concerned with: igneous rocks, metamorphic rocks, and sedimentary rocks. Today we're concerned with igneous rocks, and they're often a good place to start from because they're the rocks that form from magma. And as you can see on here, you can form magma when you melt other rocks, like when you melt sedimentary or metamorphic rocks. But in truth, the crust, the surface of Earth, is, for the most part, by volume, made of solidified magma. The continents are formed from solidified magma, and the ocean floor is formed from solidified magma. Remember how we had seafloor spreading and divergent plate boundaries where the magma is rising up and cooling to form new rock, and that's the rock that actually makes up the ocean crust. So the crust is mostly made up of igneous rocks, actually, and so we will usually start with that. And I like this diagram because it uses the Earth's surface as a reference point for a number of the processes that occur. When we talk about sedimentary rocks, we'll find that sediments like sand and mud at the Earth's surface get converted to sedimentary rock by being buried and compacted underground. And there's actually two types of igneous rock that you can form from magma. You can form intrusive rocks below ground, or extrusive rocks when the magma cools at the surface. And an igneous rock is any rock that forms when magma cools. Magma is basically a silicate soup, is what you can think of it as. It's molten rock with silica and magnesium and the other elements needed to crystallize the minerals in igneous rocks. And some magma reaches the Earth's surface, and we know that as volcanic eruptions. And a volcano, the word volcano refers to any opening whatsoever through which magma erupts. And when magma erupts at Earth's surface, it becomes known as lava. It's a bit of an arbitrary difference, but the only real difference is that lava erupts at the surface and magma doesn't. And all lava kind of starts as magma in a sense. I want to pose this question: does a volcano have to be does a volcano have to be a mountain? Does it have to be like a large cone? And in class, we've talked about some examples. No. We've talked about in class, actually, some examples where that's not as much the case. Can you think of one? It's actually at one type of the plate boundaries that we learned about. It's at divergent plate boundaries. So a volcano is a vent, but not necessarily a mountain. Remember that the mid-ocean ridges are kind of these vents on the seafloor, and in this particular case, the plates are being pulled away constantly, and so not much of a mountain builds up. The interesting thing about a volcano that is a mountain is that that mountain wasn't there before the lava showed up. The magma doesn't come out there because there's a mountain there. The lava actually cools and builds up and creates layers over time, and that's what builds the mountain. In a case like the mid-ocean ridge, where the movement of the plates is taking the crust in either direction away from the vent, the cooled lava doesn't really have time to build up. So you don't really get much of a mountain here. You get just a narrow vent. And you do actually also see this in places like Hawaii. You do also see examples of fissure eruptions in places like Hawaii or Iceland, where in many cases where you have new vents opening up for the first time, and you just have these fountains of lava coming out, but there's no mountain there just yet. Any questions so far? And again, I'm having a very hard time getting the chat window to appear when I'm in presentation mode. So probably verbalizing the questions is better until the end of the presentation. I apologize for that. I feel like about half the time it works and half the time it doesn't, and I don't really understand why, but I'm working on that. So igneous rocks come from magma, and some of them come from lava, because basically all lava starts as magma at some point, but not all magma becomes lava. Magma originates inside of the earth. Some of that erupts at the surface to become lava. Some of it just stays inside of the earth and cools to form what we know as intrusive igneous rocks, or plutonic rocks, which we'll talk about on the next slide. And one thing I want to point out, don't worry about this, but notice the chemical formulas. There we go. I can't get my cursor to show up. Not what I meant to do. Okay, the cursor isn't showing up, but notice the chemical formulas in the yellow chamber underground. You can see there's a volcanic vent, and then there's a section underground meant to show the magma chamber. And those show that magma is going to have a lot of other stuff dissolved in it. It's going to have fluids like water and carbon dioxide and chlorine in it. And then it'll also have, those fluids will also have copper and other metals dissolved in them. And actually, copper mines are often found where fluids from these magmas, like the water and the carbon dioxide and whatever else was kind of mixed in there, gets kind of, it ends up in these veins and leaves copper deposits behind. So copper mines and a lot of other mines for economically important minerals are actually originally associated with volcanic activity. And the difference between the rocks that show up at the surface versus those that show up at the bottom, or those that exist underground, ends up having a lot to do with an important texture. So extrusive igneous rocks are those that begin as magma underground, but where the magma erupts and forms lava and then cools at Earth's surface. And those are known as volcanic rocks. And that's pretty self-explanatory. Volcanic rocks are formed from lavas that came out of volcanoes, vents at the Earth's surface. And in contrast, intrusive igneous rocks form when magma remains underground. And the main difference, one of the big differences actually, is that lava at the surface is going to cool much more quickly than magma sitting underground, because is it going to get cooler or warmer as you go in deeper in the Earth's surface?
Warmer?
Yes, precisely. The interior of the Earth is a lot warmer. And so if you have just a body of magma sitting there, it's going to be surrounded by relatively warm rock inside of the Earth, and so it's not going to cool very quickly. It's going to take a long time to cool, and one thing I'll talk about is that actually has consequences for the size of the crystals. The rocks underground tend to cool more slowly, whereas if you erupt lava at the surface, it is almost immediately in contact with air, or if it erupts underwater, with water. And the air or water does a much more effective job at cooling it, especially water. And I'll have an example of, I'll have a video of showing what happens when lava erupts underwater also in here. But that causes it to cool really quickly. And when rocks cool quickly, they tend to have tiny crystals and a much smoother texture. So extrusive are those that erupt at the surface. Intrusive igneous rocks are those that form underground, that form from bodies of magma that remain underground, cooling relatively slowly, and forming what we know as plutons. And a pluton is a large body of igneous rock that formed underground. Actually, the Sierra Nevada formed as a pluton originally. granite that we now see in places like Yosemite National Park is formed as a pluton underground originally. And one thing to think about is that all igneous rocks kind of, or not all magmas start out as intrusive in a way. You can think of magmas as all beginning as intrusive. Magma always forms underground, but then some of those magmas do erupt at the surface to become lava and form extrusive igneous rocks. And I like this diagram because, for one thing, it's a cool schematic showing how, showing that the Hawaiian hotspot isn't just a single vent feeding a single volcano. They've modeled that there's a large magma chamber sitting underneath, and that there's several vents coming off from that chamber feeding different volcanoes and different fissures. But it shows you that the magma underground is connected to the magma above ground. If the magma in this magma chamber underneath were to cool, it would be considered an intrusive igneous rock, but the lava flows at the surface are considered an extrusive igneous rock, even though they both came from the same magma. And that is something to consider. In many cases, intrusive rocks and extrusive rocks can very much come from the same starting magma. It's just the big factor is where the magma ends up, like does it stay underground or does it erupt? And then consequently, that affects how quickly it cools, and that affects the texture. Questions about any of this so far? And I don't know why it's not letting my cursor indicate anything on here. I think I may need to restart my computer after class, but any questions about this? Cool. So I have some cool volcano pictures then. Extrusive rocks means lava and volcanoes. And we have rhyolite, which is formed from light-colored rock. It's from magmas especially rich in silica. And we'll talk about how color plays into this also, and how that relates to silica content. This is from the Bishop. The picture on the sort of lower middle picture is of the Bishop Tuff, which is actually in California. And a tuff is a type of rhyolite composed of ashfall from explosive volcanic eruptions. So the Bishop Tuff, which is found a little bit east, it's found east of the Antelope Valley in the Owens Valley area. That is from a gigantic eruption on the scale of the same eruption actually that made Crater Lake. And the tuff is left behind from when that volcano blew its top, basically. But not all volcanoes blow their tops. Some volcanoes have lava that just kind of flows out the vent and then cools later. You don't want to touch it, but it's not usually going to cover you and suffocate you faster than you can run away, which is why people have been hurt by eruptions in the Hawaiian Islands, but the Hawaiian volcanoes tend to produce more in the way of mafic lava flows that aren't quite as sticky and don't create these explosions as much. And so you don't want to touch the lava, and obviously it's going to stink if your house gets burned down by it, but people can usually get away from it before they get hurt. So this dark colored, the picture on the upper right is of a spatter cone in Iceland, and that's from where lava kind of splashed up and then cooled, and that's basalt. That dark colored rock is basalt. Now, you might notice that in the picture it's kind of red stained. Where does that red color? What element does that red color come from normally? We've seen that before.
Is it?
Yes, it's iron. And that's actually really important.
Iron last time, but I think it was sulfur.
The red is from iron, actually. The yellow is from sulfur, but the red, but when you have red, it's from iron. I do think my internet might be misbehaving, and I apologize if I'm hearing only parts of some people's questions. But the red is from iron, and that's actually because darker colored igneous rocks are from magmas that have, for one thing, more iron in them, more iron and magnesium. But this means that you often get red staining in basalt because the magma had a lot of iron in it to begin with. And you do actually get sulfur in these areas also. Sulfur is associated with volcanism, but that's not what's causing the red color here. Does that make sense? Any questions related to that? I am very briefly going to jump out of share mode just to see if anybody asked any chat questions. what makes, okay, I see one question in here. Anyway, let's go back to presentation mode. Okay, this is where we just were. Fantastic. So we've talked about extrusive rocks, and then intrusive rocks are those that form underground. And you might say, these aren't underground, you can see these. And yes, that's because they have since been exposed and whatever was on top of them has eroded since. And that's something you have to consider with intrusive igneous rocks. We often find them at the surface today, but only because erosion has exposed whatever was on top of them. And whatever was on top of them frequently were the extrusive or volcanic rocks formed during the same process. And the granite in the Sierra Nevada today used to be underground. It formed underground as an intrusive or plutonic igneous rock. And there was also igneous, excuse me, there was also extrusive rock on top from the volcanoes that were erupting at the surface. But those have eroded away, and so have any other sedimentary rocks on top, and it's exposed the granite pluton. And the same was actually true of the research I was doing in Antarctica. I was studying rocks from about 600 million years ago, and they were formed in a similar volcanic arc when you had subduction occurring and making volcanoes. And the volcanoes are long gone, actually, but the plutonic rock underneath from basically the cooled magma chamber that was feeding the volcanoes is still there. And the funny thing about, oh, the cursor is visible this time. That's hilarious. But the funny thing about this is that you also have these dikes, which is actually the rock I was studying in particular. They are called lamprothiers. You don't need to memorize that, but they also formed underground, actually. They formed as little intrusive sort of slivers of magma intruding into cracks or other weak points in the granite, but they never saw the surface either. And so not all intrusive rocks are big blobs. You do find smaller dikes also. Yes, I hear a question. Yes?
Would you be able to go back to where you have the definition of an intrusive
Yes.
igneous rock, just really quickly?
Yes. So extrusive rocks are formed from lavas that erupt at the surface. Intrusive are those that form underground. All set? Okay, awesome. And this is uploaded in both PowerPoint and PDF form on Canvas under the intro lecture slides section if you need to review that. Cool. And this is another shot of actually what I was looking at in Antarctica. This is all rock that used to be underground, and there were volcanoes sitting on top of this, but the volcanic rock has all been eroded away, and there's just the intrusive pluton left behind. And the thing is, what you want to remember is that you normally find intrusive and extrusive together, or at least you can kind of picture or project where the extrusive or volcanic rocks used to be. So, for example, this is Amboy Crater in California, which is out in San Bernardino County, out in the desert, and I did some volcanology research there. And that's surrounded by a gigantic lava flow where you have extrusive rocks, aka the basalt and the lava flow, and then underneath the cone, there's intrusive rock. There's the cooled remnants of the magma chamber that fed this system. This is just one case where the volcano is a bit more recent and it hasn't been eroded. And Amboy Crater is very cool if you have time to visit it. It's really out in the middle of nowhere, and you don't want to be there when it's really hot because it's miserable. But in the winter, it's a cool little day trip to take if you like desert stuff. And also, then here's another example from Antarctica where you have the granite surrounding it and then lava flow sitting on top of it. And I'm going to play this animation again, which I also showed during the plate tectonics segment, but it does a really nice job of showing how subduction is causing melting, and that melting is causing magma to form. The magma is pooling in a magma chamber, and some of that magma is erupting at the surface, becoming lava, and building up this volcano. And this is what the Sierra Nevada started as. You had magma pooling underground, which formed the granite, which is now the only part that's left, and then some of it reached what was at the time the surface and made volcanoes. But those volcanoes have since kind of been eroded away. So oops, sorry, there we go. There were a bunch of steps in there that I didn't mean to have. But the reason that the difference between intrusive and extrusive matters to this lab is because that really affects the texture. If you have rocks that where you can't really see the crystals at all, and this is how you want to think about it. Fine-grained igneous rocks are those where you really need a microscope to see the individual crystals. There are probably still crystals in it, but they're really tiny. Because remember that when extrusive rocks erupt at the surface, they come into contact with air or water really quickly, and they don't have much time, they cool very quickly. And crystals need time to grow. Crystals are very much like plants in that way. I said that rock candy isn't technically a mineral, but it does form crystals, and it's kind of like how if you try to form rock candy crystals, you're not going to get much in the way of a crystal if you just take it out after one day. You're probably going to need to wait a couple days or a week. I don't know exactly how long those take. But it's the same thing with having visible crystals in igneous rocks. And so most extrusive igneous rocks are aphanitic or fine-grained. And those mean the exact same thing. You can just kind of think of it as fine-grained. Meanwhile, the vast majority of igneous rocks where you can actually look at them and see the crystals and tell one mineral apart from another, like where you can look at a granite and see, oh, here's a black mineral, and then about a centimeter away from it, here's a pink mineral. Those would be considered to be coarse-grained or phaneritic igneous rocks. And that's where you don't have to use a microscope to see the individual crystals. And you do need to be careful with this sometimes because the dikes that I showed you previously that were intruding the granite, those are a rare example of an intrusive rock with a fine-grained texture. And that's because they actually intruded into the granite, which had already cooled by that time, and they were just cooled really fast by that. But that's kind of an exception that you don't really need to worry about for this class. And this is what I mean when I say that most fine-grained igneous rocks do have crystals. This is one of my lampriphiers from Antarctica, one of the dikes. And this is an aphanitic rock where you can't really see much in the way of distinct crystals or tell apart one mineral from the other when you're just looking at it in the field. But if you put it under a microscope, you can actually see that there's a large feldspar crystal here, and then there's a bunch of mica. This is actually the biotite, the dark colored mica that you looked at last week, and then just a lot of plagioclase feldspar within it. So the outward appearance can be kind of misleading. This rock isn't completely devoid of crystals, the crystals didn't have much time to grow, so they're very tiny. Does that make sense? And this is what I mean with the plant analogy, sort of. Crystals need time to get big. Remember that the actual starting magma isn't going to have minerals in it. Minerals are going to solidify from the magma, from the melted element, from the melted material. And over time, more crystals are going to form, but they're also going to get bigger as they add more material to them. And this last texture here in circle number 6 is what granites and other intrusive rocks often look like under a microscope, because what happened is that the magma actually had time to cool, that almost all of the magma actually formed into crystals. Something that you will see with a lot of rocks from volcanoes is that they will have crystals in them, but there's also going to be a lot of sort of amorphous, undefined, glassy space between the minerals. And remember that we do have actually volcanic glass. Obsidian, which forms from some volcanoes, is the type of glass that forms in volcanoes. Not all rocks are. There are rocks that don't have minerals in them, or that have some glass in them instead of minerals. And the point is that crystals need time to grow and get big, and also to have well-formed shapes, to have large, well-formed shapes where people can see them. So in general, most coarse-grained rocks are going to be intrusive. Granites and also Gabros. Gabros are the dark-colored rocks that make up the ocean floor. Whereas in general, fine-grained rocks are going to be extrusive, are going to be volcanic rocks. And this diagram is a cross-section of the oceanic crust, of the ocean floor. It shows how you have ocean sediments, and then you have a series of rock layers until you get down to the mantle itself. And look where the gabbro is versus the basalt. The basalt is closer to the surface, the gabbro is at the bottom. Now, this all came from essentially the same magma. This came from magma that was erupted at the mid-ocean ridge. But what happens is that the magma that's at the top is in contact with seawater, and it cools really rapidly. It forms a type of basalt known as pillow basalts, actually, because the water quenches it so fast that it causes it to cool as it's expanding outward, and it actually forms kind of a spherical pillow-ish shape, and I'll have a video of that on the next slide, actually. Now, as you go further down, the magma is further and further from the ocean water, which has a cooling influence, and then closer and closer to, well, deeper and deeper in the earth, which is warmer. And so at the bottom of the ocean crust, you have gabbro. You have this rock, and gabbro is a phaneritic or coarse-grained intrusive rock. This gabbro actually came from the exact same magma that made this basalt, but they underwent different processes. The basalt cooled really quickly, and you'll notice also this basalt has holes in it, which I'll talk about on another slide, and that those vesicles or holes are from escaping gases. But you can't really see much in the way of individual crystals. These holes aren't crystals; those are just from air escaping. Whereas these ovoid shapes you can see in the gabbro sample are individual crystals. Those are really big, pretty nicely formed crystals. And you'll notice that most of the crystals are dark colored. There are some light colored crystals in here too, and we'll talk more about color coming up. But one thing you do want to consider is that even in igneous rocks, where most of the minerals are dark colored, there will still be some. They're still based on silica to begin with, and so there will still be some light colored minerals in them. And this is the pillow basalt video. Let me bring that over. The sound is a little bit crude, I think, but this is just some video that a colleague found at one point of some people who had filmed themselves diving near an underwater volcanic vent, which seems like a really poor idea, but they survived to tell the tale just fine. So you'll see they're underwater, and you can see that there's... Turn that down just a little bit, and you can see that there's steam, because this is near where there's magma under the sea floor. And in a few minutes, what you'll see actually is that where the magma is erupting, it cools so quickly that it kind of cools into this sphere. It kind of makes this pillow shape. The water is doing a really effective job at cooling the magma and turning it to rock really quickly. And I like this video because it does show you that extrusive rocks, like these that are formed under the ocean, cool quickly because there is something cooling them. That's either going to be air or water, and water does a really effective job at doing this. Anyway, that video's in the slide if you want to check out the rest of it. It's just some cool footage. But going back to the presentation now. There are some textures that also don't directly relate to crystal size that you'll come across in this lab. So one of them is vesicular, and if you have a rock that has a bunch of holes in it, that is a igneous rock with a vesicular texture. And remember how in that previous slide, I pointed out that the magma chamber had chemical symbols on it showing that there was carbon dioxide mixed in there, and water vapor mixed in there, and sulfuric gas mixed in there. And especially in magmas where there is a lot of gas dissolved in it, where there's a lot of gas in the magma, when that gas will escape when the lava erupts and cools at the surface, and the escaping gas will form these holes, these vesicles. And you'll get in some cases basalt will often be known as vesicular basalt if it has the chemical composition of basalt and then also has these holes in it. And this is obsidian. This is volcanic glass, and this actually is a rock that has no minerals in it because the rock cooled so quickly that there was no time for minerals to crystallize. So some rocks have a glassy texture, some extrusive igneous rocks that cool extremely quickly. And meanwhile, this last one on the right is a pyroclastic texture. And you may have heard the term pyroclastic in context with really explosive volcanoes. Pyroclastic means fire pieces, like fire sediment pieces, because the lava gets kind of exploded out and thrown out in the air, and the rock formed from it is formed from the settling ash and bits of rock. And this kind of looks jumbled up. It looks kind of like, to me, like sometimes when you see that cement, like that cement that has cobblestones in it, it's kind of like that because it's just this mix of the ash and then the larger pieces of the volcanic crater itself or bits of lava bombs mixed in. It kind of looks like rubble. It looks like a bunch of rubble that's been compacted together, and it kind of is. It's the explosive material ejected out of a volcano. So questions about texture. With igneous rocks, the two main important factors are texture, because that relates to eruption style, and color, because that relates to chemistry. So I may have thrown this term around before I meant to, but there are basically three types of igneous rocks that we're concerned with. There are mafic rocks, which are more dark colored, and they're dominated by either black or green minerals. And remember that olivine, which is a green mineral, is actually considered to be a mafic mineral, and I'll talk about why that is based on the elements in it. But I find that this example of a granite is really, this is kind of a, I should have picked a better example of a granite because this is a rather dark granite, but you can see that it's kind of more gray and pink. And honestly, the presence of pink in igneous rocks is usually indicative of orthoclase feldspar, or the potassium feldspar you looked at last week, and that is considered to be a felsic mineral. And I will say that not all gabbros look quite like this, not all granites look quite like this, not all diorites look quite like this. Felsic rocks so mafic rocks will be dominated by dark and green minerals. Felsic rocks will be dominated by white minerals, gray minerals, and pink minerals. If a rock is between the two, it will be considered to be intermediate, and intermediate igneous rocks often have kind of this salt and pepper appearance to them. They have a good number of large, well-formed crystals of dark minerals, but about half of the ground mass is still, like about half of the rock is still going to be made of, or it's still going to look to be made of lighter colored minerals. And that is the thing, the darker colored minerals actually, even in Gabro, don't make up that much of it, but they stick out much more than the light colored minerals do. They tend to dominate the appearance more. So granite is an example of an intrusive rock that is felsic, and this is a slightly better example of what the texture of this particular granite looks like. This is the granite that I was walking over in Antarctica, and it is going to have some darker colored minerals in it. It's going to have some biotype maybe, but it's mostly going to be made of quartz, feldspars, either plagioclase feldspar or the orthoclase potassium feldspar, the pink one. And actually, feldspar is where the term felsic comes from. You can remember that felsic rocks have a lot of feldspars in them, and sic also kind of sounds like silica, and felsic rocks are dominated by silica. They're dominated by lighter colored minerals that have a lot of silica in them. In contrast to this is Gabro. This is actually the rock that we were looking at earlier that forms at the base of the ocean crust. And this is what that particular sample looks like. And this is not a particularly dark Gabro again. This is almost kind of borderline between diorite and Gabro, but I'd say that the mafic minerals make up a little more than half of it. And there's also green, which indicates that there's some olivine. This is a weird case where a rock that was formed in the ocean actually got shoved up on land by tectonic processes, which is not very common, and it's because normally it subducts, but occasionally oceanic crust will get stuck on land. There's some examples in the Himalaya where bits of ocean crust got kind of just stuck between the two colliding continents and then got shoved up. And those are really useful to us because it's much easier to study Gabros and learn about the ocean crust from these exposures than it is to actually go under the ocean. And rhyolite is an example of an extrusive rock that is felsic. So this is something you have to consider. Extrusive rocks can be either mafic or felsic, and intrusive rocks can also be either mafic or felsic, or intermediate in both cases. And rhyolite is formed in subduction arcs. It's actually the same thing as granite. Essentially, it's from the same magma as granite. It just cools faster because this is the magma. The rhyolite is formed from the magma that makes it to the surface and erupts and cools really quickly, in fact, to the point where you get this sort of silty, ashy texture from it. And then you have basalt, which is extrusive and also mafic. And you get basalt. You do get basalt on land sometimes. Remember that I mentioned that mid-ocean ridges often begin on land before an ocean fills them in. So you find basalt in places where mid-ocean ridges are beginning, like Death Valley. You also find them in some subduction settings. You find them at hotspots like Hawaii. And in general, something I'll touch on a little bit is that when the melting temperature is higher, the melting temperature that made the magma will be more mafic. And that's because mafic rocks have more iron and magnesium in them, and it's harder to melt substances made of iron and magnesium than it is of silica. Silica, outside of thinking about like silicon chips, if you've ever opened up one of those, if you've ever opened up a pack of beef jerky and found one of those little packages of desiccant inside, and if you actually open that up, you'll see these little beads, kind of these sort of sticky, squishy beads that you don't want to eat. That's basically what silica looks like when it's not in mineral form. And that is, you can imagine that the silica inside of those packets you get in beef jerky, that's a lot easier to melt than it is to melt a block of iron or a block of magnesium. And I want to say that igneous rock composition can be really complicated. This is a really horrifying chart that's defining a number of types of igneous rocks based on the silica content versus the amount of alkali in them, basically the amount of sodium plus the amount of potassium. And a lot of igneous petrology involves comparing the amount of silica to whatever other element you're interested in, whether it's alkali elements like potassium or trace elements. And so there's a lot of different igneous rocks that are defined by stuff like their alkali content that we're not really going to touch in this class. Like my lampropheres are defined by their potassium content, for example. This is much closer to what you'll be using in this class, and you won't even be working with all of these. I don't want you to worry too much about the term ultramafic for this class, because there's some rocks, the rocks that form the mantle actually, that are mostly entirely made of olivine and have very little silica in them at all, but we don't really deal with those much in this lab. But what this shows you is that you have composition on one axis, like composition is one parameter, and then a separate parameter is texture. And so you can get different combinations. Glass is pretty much always going to be considered obsidian, but if you have fine grained rocks, it's going to be either rhyolite if it's felsic, if it's really rich in silica, or andesite if it's somewhat intermediate, or basalt if it's mafic. And the same goes with granite, diorite, and gabbro with the intrusive rocks. And one thing, these terms, you don't need to worry about all of these, but you do see that this indicates that the mafic rocks crystallize at the mafic rocks form at higher temperatures. And they're also a lot higher. When it says high in metal cations, that's talking about, well, magnesium and iron. Mafic rocks have more magnesium and more iron in them and less silica. And something you'll find out when you learn about sediments and erosion is that they tend to erode faster. They tend to break down faster because the minerals formed at higher temperatures. Just a few more slides after this, but any questions? So anyhow, the crystallization forms minerals, and the next couple of slides talk about the minerals that we find in igneous rocks. And the igneous rocks are dominated by just about 8 common minerals. And some of those minerals are considered to be mafic and some are considered to be felsic, not because they only exclusively occur in one or the other. The felsic minerals often occur at least in some small amount, even in mafic rocks, but it indicates which ones dominate in which rocks. Mafic rocks are going to be dark colored because they're dominated by mafic minerals, dark colored black and green minerals that have a lot of iron and magnesium in them. And that's where the term mafic comes from iron and magnesium. And felsic rocks are going to be much more simply dominated by silica and oxygen without as many metals in them, metals like iron or magnesium or calcium or potassium, which is technically a metal. And silica is actually pretty easy to melt. Felsic rocks are, this is what silica kind of looks like in rock form. It forms these tetrahedra where you have a single silicon atom bonded to 4 oxygen atoms. And these silica tetrahedra are the basic building block for the silicate minerals that make up igneous rocks. Now, mafic igneous rocks will have more cases in which you also have lots of metal along with these. So these silica tetrahedra by themselves are actually pretty easy to melt. Pure substances are pretty easy to melt. But then mafic rocks are going to have more iron in them and more magnesium, and they're going to be harder to melt. You're going to have to jack up the temperature a lot more to get them to melt. And likewise, rocks with a lot of silica are much slower to cool. And I think probably a concept that one concept that is really new to a lot of people studying igneous rocks is that if you melt another rock to make a magma, it's really, really difficult to melt the entire rock. It's really, really hard to achieve high enough temperatures to actually completely melt a rock. And so if you have an example, like you have a subducting ocean plate that's going down, and the minerals in that plate are starting to melt. There is actually a defined order in which the minerals start to melt. Certain minerals will start to break down and go from being solid minerals back to magma faster than others. So the most mafic minerals are the hardest to melt. Mafic minerals are stable at really high temperatures, and so you have to melt a rock to a really heavy extreme to get all of the mafic minerals to melt. And conversely, mafic minerals are the first to crystallize when you have a magma cooling and forming a rock. Whereas the felsic minerals are usually going to be the first to melt, and they're going to be the final minerals to form. Melting and crystallizing are opposites. Melting is the solid rock melting into liquid magma, and crystallizing is the liquid magma converting into solid rock. Kind of like how I made the analogy between water being sort of the magma of ice. Water crystallizes and forms ice, and magma crystallizes and forms igneous rocks. The difference is that with igneous rocks, you have a lot of different minerals, whereas with ice, you just have a single mineral. And there's a very big temperature difference in terms of what temperatures we're talking about. So your lab will refer to a concept called Bowens reaction series, and Bowens reaction series is the order in which minerals crystallize from magma. It's also the reverse order in which minerals melt. And in general, mafic minerals are going to crystallize first. I don't think this is a chart that you've used, but this is one I've come across that I think does a nice job of showing how the darker minerals, the mafic minerals like olivine, pyroxene, amphibole, and biotype mica are going to be the first to crystallize, especially olivine, because olivine has very little silica in it and a lot of iron and magnesium. Whereas the last to crystallize will be the lighter colored minerals, potassium feldspar, including potassium feldspar, muscovite mica, and then quartz. And a lot of this has to do with their amount of silica and also with the fact that with mafic minerals, if you take further mineralogy classes, you'll see that more complex minerals have examples in which the oxygens on those silica tetrahedra, where you have the 4 oxygens surrounding the silica, they'll often be shared between different tetrahedra, and you'll have these chains of tetrahedra, and those are harder to melt. Shared oxygens make it harder to melt, and so olivine, what silica is in there, tends to exist in chains more. Same with pyroxenes. Quartz is just simple SiO4 tetrahedra, and so it's very easy to melt. And actually, this is the big reason actually why the continental crust, the crust we're walking on, is more felsic, because the crust actually originally formed from the solid mantle being partially melted. The mantle was melted, and the more felsic minerals melted more easily and formed a magma that rose to the surface and formed continental crust, which I think is really cool. And I have another chart here that you don't need to worry about everything here, but this does a nice job of showing how different minerals are present at different levels of felsic or maficness. And this shows you that, for example, felsic rocks like granite and rhyolite are going to be dominated by orthoclase feldspar, quartz, some plagioclase feldspar, some muscovite, and then very little amounts of darker micas and amphiboles. And you'll notice that on the bottom, there's a couple of parameters that show you how silica content increases for more felsic rocks, and how sodium and potassium content also goes up, interestingly enough. But iron and magnesium and calcium content go up for the more mafic rocks. And this also shows you that the mafic rocks need higher temperatures to melt them, because the mafic minerals need higher temperatures to melt. And you see that mafic rocks like Gabro and Basalt are going to have much less in the way of orthoclase feldspar and quartz. They will still have plagioclase feldspar, and something that I do want to point out here is that you'll notice that even with the most mafic rocks, the silica content doesn't get that low. 40% is about the lowest silica that you can really expect from even the most ultramafic rocks, and that is because olivine and pyroxene and the more mafic minerals have some silica in them, and also in some less extreme cases, like with just regular mafic rocks that we'll be dealing with, like Gabro and Basalt, there is still some plagioclase in them. There are still some felsic minerals in them, but they're increasingly being dominated by mafic minerals like pyroxene and olivine. Does anybody have any questions before I play this short clip for fun? This is just a little video from a project when I was actually involved with generating my own lava of sorts. We were remelting bits of lava rock, bits of basalt, and melting it again. But before that, any questions? I'm going to step out of this, just check the chat one more time. Oh, okay, cool. All right. Oops, I don't know how we ended up all the way back down there. I apologize for that, but we are almost done with the presentation. Well, that works. Anyway, it is possible to make your own lava. You just need a hot enough furnace to be able to melt rock. But this is a lava flow that was made by the Syracuse University Lava Project, which I don't know how active they are still, but when I was in college, they were doing work on modeling lava flows. They were generating their own lava and pouring it down these sort of test terrains to see how the lava behaved. And it's not perfect, because when you scale things down, it's not going to completely replicate the larger flow, but it's still pretty cool that you can do this. So today's lab is, I think it's probably not the worst thing that you have a week off after this, because this lab is a little bit longer than the previous ones. And it's not, these parts aren't all super long, and it's not clearly delineated as such, but these are basically the 4 different things you're doing during this lab. They're in order, it's just on the lab itself, they're not divided into part 1, part 2, part 3, part 4, but these are kind of the 4 different these are the 4 separate tasks that you'll be doing. So in part 1, there is a photograph of the lab tray in the actual Canvas assignment itself. There's also a link to another picture of a separate lab tray that is numbered the same but has different samples. And I really highly recommend you take the time to look at that if you find, well, actually just period, just to compare, just to make sure that something you think that you're observing about one mineral, like, oh, this one looks kind of light, is actually consistent between the two samples. Like last week, I'm very happy to look up and send you alternative pictures of rocks or minerals if you need a more clear demonstration of something. I can do what I did last week. In the second part, you identify rock colors, so whether they're mafic, felsic, or intermediate, and then in part 3, you are looking at textures, coarse-grained or fine-grained, and then whether there's vesicles, or whether there's volcanic glass, or whether it's explosive. And then the last part is identifying the igneous rocks in the tray using the resources you have, including this lab chart for igneous rock identification. So it's a bit simpler because you're really not going off as many properties as you were with minerals. With minerals, you had to worry about cleavage and color and streak and hardness. But with igneous rocks, you make an educated guess about the texture, and you make an educated guess about the color, and you work with that. You don't need to worry about all the terms here. Porphyritic is a texture that we're not really dealing with much, where you have some crystals that are noticeably larger than the others. But in any case, feel free to ask me if what you think, like if your guess about a rock lands you on something that doesn't make sense, or lands you on one that we haven't talked about much. So I recommend having these slides as well as the previous lab slides handy. There's also a couple of questions that ask you about the what elements like magnesium or silica are present in different minerals, and the chemical formulae of the igneous rock forming minerals are listed in a table in the Canvas assignment. So make sure you look there before you freak out about, oh no, I don't know what olivine is. It's in there. We're not making you memorize the chemical formula of olivine because I find it hard to remember myself. So before I stop the recording, any more questions about the lab or about igneous rocks or about any of this? All right, I'll be shutting the recording off then.